so variable, right. So probability that this variable takes some value, so we will use x equals I, right. Is we will again use lambda here as the parameter for this. So that is e power minus lambda right. So that is our Poisson definition. So now I need to find the expectation of this E of x. Harder way tutorial, easier way, well let us see which is easier, I do not know, we will try this out, okay. Let us try the Z transform for this. I wonder if I have the okay. So now the generator or the Z transform, so what is the definition for that? Summation 0 to infinity e power minus lambda lambda I divided by factorial, and this is simply z to the I, that is all, forget about all the d to the power ln, just simply z to the I, right. So we can extract e power minus lambda out, and then what do I have, lambda z to the I divided by I factorial I equals 0 to, so that is simple enough, right. So what is this right side of the term equal to, e power lambda z, right. So therefore that is e power minus lambda e power minus lambda z, which equals, again we can write it either way, but I am just writing it like this. I can make it lambda or into z minus 1 or minus lambda into 1 minus z. So I am writing it as e power minus lambda 1 by z for whatever it is worth. So that is my generation. Questions? You will save. So now what is E of x? Well, do you want to derive or just say it is 1 by lambda? Just to, we will derive, right. So it is dg divided by dz, okay, I am just dropping the x there. So set at z equals 1, right. Again for reference, okay, we will minus lambda we will just write it, it is easier to differentiate when it is lambda z, right. So what is this, lambda into parenthesis is meaningless, z equals 1, so therefore lambda. This again we said this is d square dx. then if you remember my variance is minus lambda squared, because it is, remember, variance is g of x squared minus g of x whole squared. Yeah. Therefore, your so variance and mean are one and the same, and that is kind of how you derive that. Okay, that is the part about that, and little bit some more properties that some point later on we may have to. Sometimes when you look at papers, they make these assumptions, and this is just background for reading those papers. So questions on this part? So we have seen two different MGFs and how they are used. So then, so many times, like I said, right, you have several independent random variables coming in, and there is a composite random variable, that is a summation of all those, right, in the case of Poisson arrivals and so on. So if x1, x2, xn are mutually independent, where it does come from? So there are n mutually independent random variables. So think about packets coming to a router from several links to the same queue. They are all mutually independent, and they have their own distribution in terms of number of packets per second, right? And I define the variable y, which is, right, aggregation of all those streams. So what is the, sometimes you need to know what is this distribution of this y given the distributions of x. Sometimes it is easy to figure out, sometimes it is hard to figure out. Occasionally it is convenient to use this fact that this is your convolution theorem, right. The moment generation function of m of y is simply okay, I will just spell it out. So it is simply the product of all those. Can you think of an example where you can actually use this from the variables that we saw before? Is any variable that we saw this class or last class somewhere we can use this? What variables? We saw some discrete variables last class, right. First one was Bernoulli, right, and Bernoulli is related to anything else. Geometric is also related to Bernoulli, but that is counting the number of trials until the first success, right, that is geometric, and binomial is counting the total number of successes, right. So let us see if we can use this in that context. Okay. So what is the for Bernoulli? Okay, what is the corresponding Z transform? So for Bernoulli, remember that there are two values, right, xi or x0 equals 0 and x1 equals 1, only two possible values, and the probability of 1 is p, and this is 1 minus p. Sometimes we also use the term q just for convenience. Agreed. So what is the generator polynomial for this one? Sorry, the not generator, is it generator polynomial? I don't know. Okay, Z transform. Generator polynomial is something else. So it is simply z to the I into probability of that, right. So for the two values only, right. So it is to the power 0 into x0 or probability of x0, right. So probability of x0 is 1 minus p, therefore this is 1 minus p, and this is my z looks like 2, but please pz, right, or sometimes we also write that as q plus, we write pz more because we are used to x, because your z is your variable, right, p is a constant. So we normally, since we write as ax plus b and so on, we can write pz plus q too, but we put the coefficient before the variable, so that is why we put the p before the z, right. So this is the generator for Bernoulli. Now binomial is simply n trials and I am counting the number of successes, right. So therefore if I simply, so now your binomial, right, is, if I represent the binomial as y and each of those x's were independent Bernoulli experiments, right. So therefore this is simply where xi equals 1 or 0, right, xi takes the value 1 or 0 and I am simply adding it up, right. In the case of Bernoulli, value 0, 0 or 1 with probability p or q or q or p. So therefore the, now if I want to derive the z transform for this binomial, what is it? I can derive this both ways. I can go to the basic definition of binomial and then start with that and then come back to this one, right, or it is, remember that my convolution theorem comes in handy. Now my y is a summation of all those independent variables n, and therefore the MGF is simply the product of the corresponding MGFs in whichever transform that you are looking at, right. So this is simply and now I can compute E of x. So what is the differential, what is the derivative? Yeah. Okay, I can erase them very clearly. Yeah. So what is this going to be? Again, if you want to go through the, you know it is NP, but if you want to go through the full derivation, so p plus q equals 1. So therefore when z equals 1 everything goes to 1, therefore it is n, and so forth. That is why that convolution theorem is actually handy. Okay, so I think I have covered pretty much all this. Now we will again go through some more variables. We stopped last time in the exponential and trying to see why exponential is memoryless, that we will get to in just a couple of slides. So as a roundup of all the discrete random variables that we have seen so far, we saw Bernoulli, we saw geometric, so right. This is what we have seen so far. Just a couple more to fill our knowledge of some other distributions, and then we will move on. So the next one is tied to the binomial one. Sometimes, so in the binomial what we do is we run n trials and count the number of successes, and that is distribution. But occasionally we need to know the other way around, right, as to how many trials should I run before I get n number of successes, right. That's another thing that you will also like to know, right. If I want r successes, right, how many trials should I run with the given the probability of success is p for each trial. That is called a negative binomial distribution. So that is basically the variable or the random variable representing the number of trials needed till the rth success. So I keep repeating the trials until I get r successes, right. So what will be the, so how do we derive that? Generalization of geometric is only till the first success, yeah, correct, yes, yeah. So r equals 1 would be your geometric, yeah. Yeah, that sense negative binomial seems to, but anyway it is tied to the, it still has the binomial properties, right. Okay, so let us call this variable tr. Okay, then the probability that this variable tr, right. So what is the probability of needing n trials? What is the probability of needing n trials to get r successes? See, did it from memory or derived it on the spot? Derived it, okay. Well, so anybody else want to try? So I have r successes, right. So if in n exactly n trials I need r successes, then what should I have? The last one is a success, so I should have r minus 1 successes before this one, right. So therefore it is n minus 1 choose r minus 1. So in the n minus 1 trials preceded this one I have r minus 1 successes, and so out of which r minus 1 was successful. This is only for the n minus 1 trials, right, q right. The last, there should be one more p you are saying, right. I looked at it and said why is I looked at the book to see why that p is not there, but that is because we are assuming that the nth trial is a success, right. So this is conditioning on the fact that your nth trial is a success. I couldn't, okay, see what we are trying to do is this, okay, this is the for having r minus 1 successes in n minus 1 trials, right, given that the rth trial is a success. So that will be into the probability that rth one is a success, which is p, then divided by the fact that this is all success. I think your p and p will cancel out to do conditional probabilities. We will work out the derivation later. Yeah, this is a conditional probability that your rth trial, or nth trial is a success, right. So nth trial is a success given that you have, or no, what is it?
No, but this is the probability you take n trials for
Too far, yes.
This is what the
Random
is
is
defined as.
Yeah.
Then it should be. Then it should.
Then
there
you
is
have
a conditional there.
we have this extra 1p is what you are countering, right. Okay. I looked at Jain's book. Jain's book defines it slightly differently, where he said there is a modified the same thing. Sorry, in his definition, he is looking at the total number of failures x before the mth success. Same thing, right? Total of m success, so m plus x trials is what is there. There the term is correct, p to the m and 1 minus p to the x, right? In this particular case, this because you are only looking at those. This is the combination of having r minus 1 failures or r minus 1 successes and n minus 1 trials, and that is what we are reporting in this particular case.
But this is a conditional probability because we are considering r minus 1 successes only.
Yeah, only
Condition that the
nth trial is a success.
trial is a success. Yeah. So that nth trial success is already given.
Yeah. So that is why you are only looking at this is the number of ways in which you can have. Say this is what is this. This is the number of ways in which you can have, because you can't see what I am pointing here, right? Number of ways in which you can have r minus successes and n minus 1 trials, right. And therefore in there, which means the nth trial is effectively a success. Still not convinced? Okay, fine. We will go back and to check with the basics for derivation of it, right. So that missing p we will figure out, right, as to where that how to get rid of that p.
So what is the probability of getting
Having
n successes in
no r successes in n trials, yes.
Which is the probability of getting n minus 1 successes, r minus 1 successes in n minus 1 trials,
And
into
the
probability of getting a success in the final trial, given that we have got r minus 1 success in n minus 1 trials. But we are assuming these are independent events.
Yes.
So probability of success on the final thing given this is equal
Is
to probability of success on the final thing, which is p.
P. Okay.
So that it will be multiplied by p.
Okay, but then when if you are doing conditional probability, right?
But this is not a conditional probability.
Okay, we will derive. We will come back and fight this out, right? Okay, so why missing p? That's what you are asking, right? I will leave that there. Okay. Then there is another, this hypergeometric is there. You might wonder why are we looking at many of these things, right? Some of these things we might never encounter. You never know. Sometimes you will need it. If you look at gosh, in one of the congestion control algorithm derivations, actually we use something like this. This probability to find out, right, in case how many trials are needed and so on. This is in some old Schwartz book derivation is there, right? Or actually trying to find out the performance of throughput of a windowed congestion control system, window based mechanism, in which sometimes we end up having to use this. So anyway, this is again just for now it just looks like generic knowledge, just store it away, and in case you ever encounter this in a real system, then this will come in handy, okay. But this is also a standard, this is useful in where are we in 12, okay. See, some of the analysis is for performance, sometimes is also from reliability perspective, right. So we are only looking at, we have talked about 3 types of performance metrics, right. One is that speed, the second is reliability, right, and the third one was related to availability and so on. So reliability measures require such kind of distributions, okay. So we will look at this case where you have a box of, let's say 1000 whatever toys, and you want to find out, that probability of that 10% of these toys are always faulty, right. That is measured over years, so there is a definite probability that some d out of these 1000 toys are faulty, right. And then your job is to pick, right, have somebody randomly pick toys, say up to some stuff, you can't pick all 1000 and check whether they are faulty or not, right. So you have to pick say only 10 or 100, test them, right, and then put it back, and then say you take it out of the box. So you take one, it is this is without replacement, yeah. So if it is defective, you take it out. Anyway, you take it out. If it is defective, you throw it aside, right. You basically have to put it in 2 piles, and you want to hope that within 100 of your testing that you have basically found majority of the defective items, right. That is one way of looking at it. Makes sense, right. You don't want to test everything. This is again testing when it goes, right, sampling. You are doing a sampling, a test, and see, you want to maximize the probability, right. You won't get 100% all the defective items, so some defect will still go through your next QA, whatever it is, but you want to maximize the probability of detecting as many items as possible, right. That's where this hypergeometric will come in handy, okay. So suppose there is a box with n say items d, right, d are defective and that d is some either known or it is simply guessed based on past information. You know that some a fixed fraction of n is being defective, therefore okay maybe 10-15%. So the d is some fraction of this n that you know. Okay. Then you select a random sample of n items where n is definitely should be less than, if equal to n, that means you are testing everything, but you do not want to do that, right. This is your sample testing that you do, and n should be really much smaller than n, right, but for now we know that at least it is less than n, right. Send the probability, so h, right, of getting k, finding out what is the probability of detecting k faulty components or faulty items, given that you are done n samples, d is the total number of defective items, n is the total number of items in the box, right. So this is the probability of choosing without replacement. So once you sample, you throw it outside, you do not put it back in the box. We will not derive this today, I will simply give you the expression. So that is given by choosing So we will just do one quick example to see. So if I have n equals 20 and I know there are 4 faulty items in there and I choose, right, 10 items from the box and I do not put them back, and I want to find out the probability that I found 3 defective ones, because my goal is to get rid of the defective ones. Yeah, n minus k should be 17, right. I might have must be small n minus k, must have got that wrong. So what does it tell you? That with only 10 samples, right, it is pretty difficult to get here. Even 25% of the time you will not be able to find even 3 defective items, forget about all the 4. So your systems, right, will have fairly large number of defective items will keep going, but that you deal with in warranty phase or whatever next quality control phase. Okay. Questions? So this is again just for storing in memory for now, okay, but this is without replacement, right. So I take an item defective or whatever, I set it aside, but if I throw it back in the box, right, and I keep sampling, then what does it become? It becomes a binomial, right, because that is with replacement, because your probability of finding a defective item is always the same, they are always d by n. So every time you look for something, it is always d by n, and then finding out whether here your success is basically finding a defective component, right. So therefore for large, when your n is substantially smaller, right, then if your n is very large, then this basically so k n trials, so getting k successes in n trials with the probability of success is d by n, right, we will simply approximate here. So you can use the binomial as a short form, shortcut instead of using this other. That's it.
Can you explain the range of k?
Which one?
The range that you had given max.
Oh,
That's basically that second.
this one, second part, right. So why do we need? Okay, yeah, this one is evident. Okay, so the lowest possible value for k, right. Yeah, so you have n, okay, your n minus k, right, n minus k should be less than or equal to n minus b, right. So from that you will get your, I am pointing there. So here, right, it comes from this condition that n minus k has to be less than, that is from the formula point of view, but from the actual physical point of view, let us see what should the number of defective elements should be at least as large as your sample size plus the total number of defective elements.
The number of non-defective items should be.
Yeah, okay, let us see.
This is like lower bound of the non-defective items that you can choose.
The number of non-defective items is n minus d.
N minus d. You
right?
cannot choose.
You cannot choose more than
n minus d.
I don't understand why it's a lower bound. D plus n minus n.
Okay. Yeah, let's see.
It's non-defective, right?
So there it is.
That's what I'm saying. If k is 0, then the number of non-defective items you're choosing will be greater than non-defective items in the set.
So in this particular example, if you look at it, it is 14 minus 20 is minus 6, right. So you cannot have, therefore it cannot be negative. So where will it be case when we have, if everything is defective, right. So it is n is defect 20, d is also 20, then
If you're saying like 20 out of 20 samples, you're saying 15 are defective, and you're saying I'm
choosing 10 from it, you can
so
only
no,
max
yeah,
get 5.
right, yeah. So you can only, it's either max of the total number of samples that you choose, right. So that will be n, right, plus d. Okay. Let me just write this on paper and figure it out, right. I will come back to you with the physical explanation for that. Okay, the last one, then we will stop and then we will go over the tutorial today. So this is uniform, right. Uniform discrete random variable, there is continuous also. So there are two ways to look at uniform. Either you have a set of items, right, x1 through xn. So all possible values are x1 through xn. This is the set of possible values for the random variable, right. So x can, and the probability of xi is simply 1 by n, right. If this is so called image is a set of, right, these possible values that it can take, and 0 otherwise. So this is one form of uniform distribution, which means all possible values are equally likely, right, which is normally the case when you have an enumerated set. It is not a continuous set of numbers or a discrete set of integers. So that is one form of uniform distribution, and the other form is where you have right. So the x can basically be between, say, b and some value a, right. So all possible values are, so from a to b everything is possible. So you have a total of how many items? B minus a plus 1, right. So the probability will be b minus a plus 1. This is only integers, right. This is a discrete random variable. So the probability of so xi is and this is also useful. I mean, this is very simple variable. Okay. Okay, so that ends the theory part.